Students of class 12, Assalamu alaikum. How are you? I think all of you are well. Welcome to our today's online class. I am MD Asghar Khan, Senior Lecturer, Department of Mathematics, Milestone College. Okay, this is our second lecture of exercise 9b. Today we want to discuss about example 4. So that for a particle moving with the uniform acceleration f in a straight line, f is equal to this, where s is the space described in t second and s prime during the next t prime second. Okay, at first we want to draw a straight line where the particle moving along this line. Okay, let A be first the particle moving as distance with t second. So here is their starting point, and after t second, then he will reach this point is b, and velocity also at this point is b, and inertial velocity at a is equal to u, and then the distance is s, and s prime during the next t prime second. Next t prime second, then the particle move to the point C by the t prime second, and distance is s prime. We have to prove this. The uniform acceleration is this. Okay. Given, let the particle move with CTU from point A. Just the particle move with the initial velocity u from the point A. Okay. Here AB is equal to S. Velocity at point B is equal to V. Okay, and time is equal to T. Again distance, again for time t prime, BC is equal to S prime. Okay, now this is our description for whole journey of this particle. Now we want to apply the formula for equation. We want to apply the equation of motion for AB and also for BC. At first for AB. Okay, for AB, this is the terminal or final velocity. V is equal to u plus f t, because f is a uniform acceleration for whole journey. Okay, and s is equal to another equation. This is equation 1. Another equation, s is equal to ut plus half of ft square. Okay, just s is equal to, taking t as a common, then u plus half of ft. Okay, so s divided by t is equal to t transfer into right hand side, then s divided by t is equal to u plus half of ft. This is our equation number 2. Okay, this is our equation number 2. Now for BC we want to apply this equation of motion. Okay, now for BC, okay, now for BC, we get from the formula s is equal to ut plus half of ft square. Here s is equal to s prime. U, that means initial velocity for BC is equal to b. bt plus half of time is t prime and half of ft prime square. Then s prime, taking t prime as a common, then v plus half of ft prime. Here by using equation 1, v is equal to u plus ft. Then s prime is equal to t prime, v is equal to u plus ft by using equation 1. Using equation number 1. Okay, then s prime divided by t prime is equal to u plus ft plus half of ft prime. This is equation number 3. Now we need s prime t prime minus s divided by t, and this expression we can get from equation 3 minus 2. Then we get this expression. So we want to subtract from 2, subtract equation 2 from 3. Okay, so we get from equation 3 minus 2, we get from equation 3 minus 2. Okay, so s prime divided by t prime minus 2 minus 3 minus 2 is this. This is equation left hand side of equation 3 and equation 2. Then ft minus half of ft. This is 1 ft. This is minus half of ft. So 1 minus half is equal to half, and this is half of ft prime. Then here s prime divided by t prime minus s divided by t. Okay, s prime divided by t prime minus s divided by t is equal to half of f is common, then t plus t prime. Okay, then this half transfer into left hand side is equal to 2 into s prime divided by t prime minus s divided by t is equal to f of t plus t prime. We need the value of f, so f into t plus t prime is equal to 2 into s prime t prime minus s divided by t. Then f is equal to 2 into s prime t prime minus s divided by t, t plus t prime. This is our proof of uniform acceleration f. Now example 5. V1, V2 and V3 be the average velocity in the three successive interval of a time t1, t2 and t3 respectively of a particle moving on a straight line with uniform acceleration. So that this is our expression. We want to prove this. Okay. This is our total journey time A to D from time t1 starting at a point A with initial velocity u, at point B u1, at point C u2 and at point D u3. Uniform acceleration is f. Okay, let the particle moving with CTU from the point A. Uniform acceleration and uniform acceleration is f. Okay, the velocity at B, C and D, velocity at B, C and D are u1, u2 and u3. respectively, and the three time interval t1, t2 and t3 time for AB is equal to t1, BC is equal to t2 and CD is equal to t3. This is the description for whole journey. Okay, now we get from the equation of motion, we get from the equation of motion B is equal to u plus ft. Now from AB, for AB V is equal to U1. U is U. F is always equal for all time interval, and this is T1. Okay, equation number 1. Okay, for BC. Okay, here for BC terminal velocity is U2, so B is replaced by U2, and the inertial velocity is U1. F is always equal, and time is T2. Okay, here U1 is equal to, by using 1, U plus Ft1 plus Ft2. This is from U2. Okay, this is equation number 2. Okay, now from CD. Okay, for CD, here V is equal to U3 is equal to U is equal to U2. F is always equal for all. F time is T3. U2, by using equation 2, U2 is equal to U plus Ft1 plus Ft2 plus Ft3. This is our equation number 3. Okay, we have a 3 equation. Just V1, V2 and V3 are at the average velocity for V1 is the average velocity for AB, and V2 is the average velocity for BC, and V3 is the average velocity for CD. Okay, now we get V1 minus V2. Okay, now V1 minus V2 is equal to, okay, V1 is the average velocity for AB, so U plus U1 divided by 2, this is the average velocity for AB, and V2 is the average velocity of BC, which is U1 plus U2 divided by 2. So U plus U1 minus U1 minus U2. After this we get U minus U2 divided by 2. This is our B1 minus B2. Okay, this is B1 minus B2. Okay, now B2 minus B3 is equal to, B2 is the average velocity for BC, U1 plus U2, U1 plus U2 divided by 2 minus B3 is the average velocity for CD, U2 plus U3 divided by 2. So U1 plus U2 minus U2 minus U3. Okay, then U1 minus U3 divided by 2. Okay, now from left hand side, divided this by this. Okay, therefore V1 minus B2, B2 minus B3. So this expression is divided by this. So this is equal to U minus U2 divided by 2. Divided by this is U1 minus U3 divided by 2. So U minus U2 divided by 2 into 2 divided by U1 minus U3, and after this we get from this expression we get okay, so V1 minus V2, V2 minus V3 is equal to U minus U2 divided by U1 minus U3. Okay, now from equation 1, 2 and 3, U minus U2 is equal to U plus ft1 plus ft2. Okay, then here U is U and U2 is equal to, from equation 2, U plus ft1 plus ft2, and U1 is equal to U plus ft1 from equation 1. Okay, and U3 is equal to U plus ft1 plus ft2 plus ft3 from equation 3. Then U minus ft1 minus ft2, so U plus ft1 minus U minus ft1 minus ft2 minus ft3. Okay, then okay, ft1 minus ft1. Okay, then taking minus f as a common, then t1 plus t2, and here minus f is a common, then t2 plus t3. Okay, so we get b1 minus b2, b2 minus b3 is equal to t1 plus t2 and t2 plus t3. This is our proved or should. Okay, this is example 5. Example 3, two trains on the same line are approaching to another with the velocity u1 and u2 respectively. Then first train starting from point A with velocity u1 and second train starting from B with velocity u2, and there is a distance between them is seen from the other. If their distance is x, then two trains in each other. Okay, their middle distance is x, then two trains in each other. Okay, if they apply the highest retardation, okay, then they need retardation, because two train will be stopped between the distance x, otherwise two train fall into collision. Okay, so their retardation is f1 from first train, and retardation to second train, I mean train B, the retardation is f2. Okay, so that it is just possible to avoid a collision, just possible, that means the collision, the highest distance. What is highest distance? For train A and B will travel, then to avoid collision, this is just possible, then their highest distance traveled by two train is x, their highest distance, and then this is called as just possible to avoid the collision. And it is possible to avoid the collision because then two train, after seeing their position, then two train will travel x, but then two train can travel x or less than x, not greater than x, not greater than x. That means the two train avoid collision, possible to collision, then their traveling distance must be less than or equal x, then they can avoid a collision. Okay. Now description. Let the velocity for first train is u1 and second train is u2 at point A and B respectively. Okay. Uniform retardation for first train. Then their highest retardation. So retardation for first train is equal to f1. Okay. And retardation for second train is equal to f2. Okay. Then their for both them their final velocity will be 0 because they will stop at any point to avoid the collision. Okay. Now we want to apply the formula. This is retardation for first train and second train. Okay. Now we want to apply the equation of motion. We get from equation of motion v square is equal to u square plus 2fs for the first train. Their final velocity, because it has a retardation, so this sign will be negative. Okay. For first train, inertial velocity is f1. So their final velocity is 0. So 0 square is equal to u1 square minus f is f1. Let the for first train the distance is s1. Distance for first train is equal to s1. Okay. Then we get 2f1 s1 u1 square. So s1 is equal to u1 square divided by 2f1. Okay. This is s1, value of s1, u1 square divided by 2f1. Now for the second train, apply this equation of motion for the second train. Okay. Then okay, inertial velocity is 0. Then final velocity is 0. Inertial velocity is u2 square minus f is f2 and s2. Let distance for second train is equal to S2. Okay, so 2F2 H2 is equal to U2 square. Then S2 is equal to U2 square divided by 2F2. Okay, this is H2. But 210, the total distance for 210 is X. Okay. Now they are together 210, their distance is X. So S1 plus S2, their highest distance, for just possible to avoid the collision. Then just possible, it is possible if their highest distance covered by 210 must be is equal to X. Okay, otherwise then 210 fall into collision if their travel distance not greater than X. Okay, so S1 is equal to U1 square divided by 2F1, S2 is equal to U2 square divided by 2F2 is equal to X. Okay, so from this, half is our common, U1 square divided by F1 plus U2 square divided by F2 is equal to X. Then U1 square divided by F1 plus U2 divided by F2 is equal to this half transfer into the right hand side is equal to 2X. Okay, so F1 F2 is our LCM, U1 square F2 plus U2 square F1 is equal to 2X. So U1 square F2 plus U2 square F1 is equal to 2 F1 F2 X. First condition is proved or should. Okay, first condition is proved. This is our first condition. It's just possible to avoid the collision. Now it is possible to avoid the collision. It means their distance, their traveling distance less than or equal X. Okay. Now for the second condition, we can change from this step. Their middle distance is less than or equal X. Okay, so S1 U1 square divided by 2F1 plus U2 square divided by 2F2 less than or equal X. So we can write it similar calculation. Okay, is less than or equal 2X. Up in right hand side it will be 2X. Then F1 F2 U1 square F2 plus U2 square F1 is less than or equal 2X. Then U1 F2 plus U2 square F1 is less than or equal to 2X F1 F2. Okay, this is true of condition 2. Okay, my dear student, this is our today's class.